We are very happy today to have Pushkal from Harvard. He will tell us about semi-classical microstates. Please.
Thank you, everyone. Good afternoon, and thank you for inviting me for this seminar. It's the first time I'm visiting University of Chicago, and I'm excited about talking to all of you about some of the recent work that I've been thinking about in collaboration with Daniel Jeffress, Sarah. Sarah is a PhD student at Harvard, and Troy was an undergraduate. So it's an ongoing work, and we have been thinking about this idea, and I would like to present you some of the preliminary results. So let's dive right into it, and please let me know if I'm going too fast or slow, and if you have questions at any point. So the background and the motivation is basically trying to understand the phase space of black hole microstates. So the problem is the following. So let's say we start with black holes. For simplicity, let me consider A as black holes. Now I can construct, I can foliate the space-time using Cauchy slices, which have the nice property that the curvature everywhere is finite, and these slices it seems that we should be able to define semi-classical excitations on these slices. But as we move these slices upward, what we find is that the volume of the interior grows. By that, what I mean is that the volume of the region behind the horizon grows. Now, that in itself is not a problem. I mean, so it grows without one, so it can grow to infinity. But that in itself is not a problem because volume outside the horizon is also infinite. But now consider an excitation which is behind the horizon now. An excitation behind the horizon can have negative energy when measured from the boundary. The reason is very simple. So if you look at some excitation outside, let's say an excitation here, let's say some particle trajectory here, this trajectory will always move forward in time. So if I measure the energy contribution of this trajectory from, let's say, the boundary, I always find that it's positive. But a trajectory in the interior but inside behind the horizon, the time and radial coordinates will switch roles. So trajectory in the interior with respect to the Schwarzschild time could move either forward or backward, and that's rough intuition of why you could have negative energy excitations behind the horizon, where I mean energy when measured from the boundary. In fact, we can look at the scalar field, and we can decompose the scalar field in terms of modes, I'm thinking of these modes as being defined completely behind the horizon. So the ingoing modes are the usual modes. So if you think of stuff that we throw from outside, so these would be the ingoing modes. But these outgoing and these ingoing modes will have positive energy. But these outgoing modes, when we see the try to write on the commutator of these outgoing modes with the boundary Hamiltonian, you'll find that it has the wrong sign. And so coupled with this fact and the fact that at late times the slices, the volume of the interior grows, we find the following issue. So suppose we define an ensemble by fixing the energy as measured from the boundary. That ensemble, it seems that that even with semi-classical excitations on top of this background, we find that ensemble has infinite phase space volume. So, but how is that consistent with the expectation that the entropy of black holes should be finite and should be in fact proportional to the area? So that's roughly the overarching theme of the talk. Of course, I'm not going to tell you why it's finite or why it's proportional to area. In the talk, I'm just going to try to, I just want to understand whether we can approach this infinity in a better way, whether we can have a better control over this infinity. Right. So if we assume holography, then there is a potential resolution for this, and the resolution basically it boils down to the fact that the boundary theory has finite number of degrees of freedom. So if we look at states overlap between seemingly independent states, let's say an excitation here and an excitation here. So those states in a local field theory, we would assume that they are completely independent, but it's often expected that these seemingly independent states will have some non-trivial overlaps, which would be suppressed by the entropy of the black hole. But again, that argument has to do with the fact that this boundary theory has some finite number of degrees of freedom. So it's not completely satisfactory. We would like to understand if there's a bulk mechanism which could explain why there could be such an overlap, or why the entropy should indeed be finite and not divergent. I mean, if there's any question at this point, otherwise I'll move with the setup.
Yeah, more precisely, the boundary theory has an infinite number of degrees of freedom, but a finite density of states at fixed energy.
Oh, so when I say that the boundary, yeah, that's right. So I meant that in the microcanonical ensemble, when we have fixed the energy at the boundary, then it has finite degrees of freedom. Yeah. Otherwise, it has infinite degrees. Right. Okay. Okay. So the setup that I'll work with would be super simple. It would be JT gravity with dynamical end of the world brane. We'll start with this. We'll later add some matter excitations. Right now, it's just this. Now we can write down the action. So the action has the usual JT term, phi is the dilaton. Plus we have the contribution from the boundary of ADS. And then we have some contribution from the end of the world brane. U and V are fine parameters in the boundary and at the brane. So S naught is if you think of this this theory as dimensional reduction from a higher dimension near extremal black hole, then S naught is the extremal entropy. Kappa is 1/8 by G Newton. I'll set this to 1. Right, but it's not super important for me that it has a high dimensional interpretation, but I'll just focus on a 2D theory. So most of this talk would be about just black holes and this kind of a setup. Okay, so we can look at the equations of motion. When we vary the dilaton, we simply get R plus 2 is 0. And
K is extrinsic curvature here, or?
yeah, that K is the extrinsic curvature. Yes.
And the K in front of the whole square brackets is a Newton constant.
That's the kappa.
That's the kappa. I'm sorry, it looks very similar. That's this.
Okay.
Yeah.
What is mu?
Mu is the mass of the end of the world brane, tension on the brane. So that's a parameter of the theory from my point of view. It will be clear in some time where the brane is, what's the geometry. Just bear with me a little bit.
Do U and V here now, or you haven't specified anything about U and V? What are the coordinates, U and V?
No, so U and V are not, so these are time-like coordinates. These are, so U is the affine parameter on the ADS boundary, and V is the affine parameter on the end of the world brane. Okay. So yeah, those are not null coordinates. Any other question? Okay, so now we can also look at the dilettante equation of motion. That's also extremely simple. Right, and we can solve this equation, the first equation that just fixes the metric, so I'll choose a coordinate system where the metric looks like this. And the general solution for the dilettante takes the form sine sigma. So these are my solutions. Now I'll explain the boundary conditions that we need to impose. So on ADS, we'll impose traditional boundary condition. We will fix the metric and we'll fix the dilettante. Where we use the affine parameter as I described before, we want the metric to take this form near the ADS boundary and dilettante to be this, epsilon is small. But at the end of the world brane, we want gravity to be dynamical. So the way we'll do is, so what we want is that when we vary the action that, so we obtain the corresponding boundary conditions by demanding that the variation of the action dies. There's no variation contribution coming from the end of the world brane. Basically, this was ADS. At the end of the world brane, what we'll get is that this should be 0, where n is the normal to the brane, and also that the normal derivative of the dilettante at the end of the world brane should be related to the mass of the brane. All right. So these are the boundary conditions that I want to impose. Now we can look at the gauge symmetries.
Just to make sure I understand.
Yeah.
Where's the condition for the normal derivative? Correct. Why is the normal derivative delta related to mu?
Right. So when I vary the action, so I'll get a contribution. I'll get a term which would be an integral over the end of the world brane, and I don't want. So what I want the end of the world brane to be dynamical. I don't want it to contribute to the Hamiltonian. So I want the variation to be killed at the end of the world brane, and that will give me this contribution. So it's basically telling us that, so think of the end of the world brane as a particle. So it's basically the back reaction of that particle on the dilettante. And I mean, in fact, if you had a particle, as I'll introduce later, what this equation is actually telling you is that suppose there's a particle trajectory, there's some dilettante profile on the right, there's some dilettante profile on the left. What we want to do is that we want the dilettante profile to be continuous when we are matching the solutions across the particle, but we want the jump in the derivative to be proportional to the mass of the particle. And since this is the boundary condition on the end of the world brane, there's nothing on the left, so that's just 0, and that's why I just get like the derivative, not the jump. Okay. So the gauge symmetries here are basically the isometries of ADS2, and I'll fix the isometries of ADS2 to get a particular form for the dilettante, and in those coordinates I'll draw the Penrose diagram. I'll draw the a trajectory of the end of the world brane, so that all of this is much more clear. So to do that, let me define these coordinates, which are embedding coordinates. I'm embedding the ADS 2 in higher dimensional R3, and so the reason why I want to do this, and also the ADS2 hyperplane would be minus y minus 1 square minus y0 square plus y1 square is minus 1. The metric in the embedding space would be minus t minus dy0 square plus dy1 square. Let's talk about. All right. Okay. So yeah, and it's clear that the isometry is SO2, 1. So in fact, in these using these definitions, I can rewrite the dilettone solution as V mu y mu, where V mu is just A sine D, A cross B. I'm doing this just because I want to later rotate the coordinate system and get a very simple form for the dilettone. Similarly, I have not told you where the end of the world brane is located, and that comes from the equation that grad A n A is 0. If we solve that, what we'll find is that the end of the world brane is located at cos sigma equals r cos t minus theta, where r and theta are parameters parameterizing the location of the brane. In fact, this equation also I can write in a very simple form. I can write this as u mu y mu equals 0, where u mu is just r sine theta, r cos theta, and 1. So now I'll gauge fix. What I'll demand is that V mu is 0 phi h 0, where phi h will be the extremal value of the dilettone. But when I do this, I still have SO1, 1 left, which I'll use to fix set theta of end of the world brane to 0. So u mu will be 0 r end of the world brane. Now this r is related to the boost of the trajectory, boost of the end of the world brane, and since we want so this will basically give us the dilettone solution is phi h cos t over sine sigma, and as we discussed, the location of the brane is just cos sigma is cos t.
So in what sense is this a gauge symmetry? It looks like you're just embedding ADS2 into ADS3.
Yes.
Sorry, ADS2 into Minkowski 3.
Minkowski 3, yes. So it's gauge symmetry for the 2D theory that I started with. What's the question?
The question is, I guess, right, you're just saying there's some hyperboloid in Minkowski space.
Yeah.
Right, which has an ADS2 metric.
Yeah.
So I wouldn't call it a gauge symmetry, I'd call it an embedding.
So that's an embedding, you're right. But now I can choose a different embedding by rotating the coordinates t and sigma. So rotating y
So
one
there's a
y.
freedom to the embedding, which is just Lorentz transformation.
But
Yes,
if you fix the
exactly.
particular embedding, you fixed the gate, the SL2R.
Yeah,
Okay.
right.
Okay.
So and in that particular, so when I do that fixing, so I get a particular solution for the dilaton. So from the point of view of 2D theory, I'm fixing a particular coordinate system in which the dilaton has this profile, and the end of the world brane is located on this trajectory. That's it.
And that trajectory does what as, I mean, if we sketch this on a Penrose
Yeah.
diagram,
I'll do
what does
that
it look
now.
like?
Yeah. So on a Penrose diagram, this is the location of the ADS boundary. So in our coordinates, this would be pi over 2. This would be minus pi over 2. This point here would be sigma here is pi is 0. This is the horizon. This would be the location of my ticket point. In this coordinate system, it's the location is just t equals 0 and sigma equals pi over 2. The end of the world brane will be symmetric around this t equal to 0 slice. This is the end of the world brane. Right, so that's the Penrose diagram. The region of interest would be basically, so on physical grounds, we want phi naught plus phi to be positive. Then if you impose that, then the region of interest would be something like this region.
And that's for a particular sign of mu?
Yes, that's for a particular sign of mu. So this is when mu is positive.
People did something very similar to this back 30 years ago when they were looking at the CGA test model, where you think of in that case, you have sort of linear dilaton geometry, and you think of the end of the world as basically being the origin of space.
Yeah.
And again, you treat it as a dynamical moving mirror, and you ask what questions about what happens if you throw in some matter. So typically what happened was that that boundary of space would accelerate away. And that presumably is because people were working with a different sign of mu.
So
The way you made black holes was basically you had a dynamical moving mirror, and as usual, if you have a mirror that's accelerating away from you, it looks like there's Hawking radiation. If I look at the vacuum.
So here, what I want to do is, maybe you're thinking about a scenario where the end of the world is like this.
Well, actually, I was thinking more like, yeah, something like that.
Yeah. So we don't want to. So that would be the case when mu is negative.
Mhm.
We don't want to consider that because then the end of the world brane would be visible from the boundary. So in this setup, since this is the horizon, the end of the world brane is always behind the horizon, and I want to think of this as a proxy for a black hole. So my boundary is here. And yeah, I want to think of this as a proxy for black hole in my two-dimensional theory.
Okay.
Okay, so right, so we can now try to understand the phase space of phase space of this setup. So we can parameterize the phase space by the boundary location. So let's say I use U naught to kind of specify the location of the initial slice. So U naught is basically the affine parameter on the boundary that's related to the coordinate t as follows. And you can see from here, as U goes to infinity, t will go to pi over 2 and minus pi over 2 when U is minus infinity. So and we can determine the Hamiltonian. The Hamiltonian will have a very simple form. It will just be phi x square over 2 phi b. And so the symplectic form would simply be del h del u naught. And from here, what I want to emphasize is that suppose I look at an ensemble where I fix the energy and compute the phase space volume, we'll get a divergent answer because of the u naught integral. And that divergence is related to the fact that at late times, length of the interior grows without work. That can be made precise. So, let me define. Let me be clear about what I mean by the interior slice. So U naught is basically a proxy for the initial slice. Now, I can consider a foliation of the spacetime with geodesics which fall orthogonally on the end of the world brane. So that's a well-defined way to specify a geodesic. The length of this geodesic we can find the length of this geodesic, and that length is given by this formula. So this is like the length of the initial slice. And as I take U naught to infinity, and T naught here I'm defining as E of U equals 0. The length will diverge because of this term. So this is the familiar increase in the length of the interior at late times. And so the divergence in the phase space volume, which was coming from the integral over U naught, can also be thought of as divergence due to the increase in the length of the geometry, the length of the initial slice. So this suggests that if we want to define if we want to get a finite phase space volume, then fixing the energy is not sufficient. What we can do additionally is we can fix the length of the initial slice. This will not fix the length at all times, of course, because at late times the length will always grow. But if we also put a bound on the length of the initial slice, that will restrict this, restrict the integral over a finite range of U naught, and we'll get a finite phase space volume. Is that part clear? Okay. Okay, so far I haven't done much. I haven't included any matter excitation. So this is not even beginning to answer the question that I was talking about earlier, where we were discussing semi-classical excitations on a background. So I want to approach that now. So I want to understand whether a similar procedure would give me a finite phase space volume, even if I have some excitations in.
So I'm still a little confused about the last point. So,
Yes.
So I thought on the initial slice, you've got a cutoff on the ADS boundary, and you've got the end of the world brane, defining, anchoring some point in the interior. So the length of that slice is finite at any time, right? It's just that it's growing.
Yes.
So, in what sense do you not like, why do you not like that? Or what's the problem? I mean, there is no, it's not clear that that's a problem, right? So your phase space is basically two-dimensional, right? There's the coordinate L and U naught and H. So, it's, all you're complaining about is that you're being driven to some particular point in that phase space. There's not like some huge number of states here that you have to worry about, right? Because it's all topological.
Yeah, that's true. Right now it's topological. I'll add matter now, but even here so if we just fix the energy, if we just impose this condition and try to understand what is the what's the volume of the phase space that corresponding to this ensemble, that's infinite, right? Because of U naught. Because even if we fix the energy, which will basically fix the fix phi h, when I do the integral over the symplectic form, I do have a divergence from integral over U naught, right? So that's the only point I want to drive.
Are you saying that the wave function is not square integrable or something? I mean, I'm confused. There's a classical saddle point, which has a fixed finite U naught. So are you saying the fluctuations around that cause some kind of divergence in?
No, what I'm saying is that I could have chosen, so when I change U naught, I want to think of that as a different solution, right? So
Changing U naught, but U naught's conjugate to H, so why isn't it just a time variable? Why isn't changing U naught just time evolution?
So U naught was right. That's
So I agree with you that I guess that U naught has an infinite range, but that's just because time goes from minus infinity to plus infinity.
right. So what I had in mind was that so U naught was basically specifying the location of the initial slice. So I mean, for instance, if we if you look at the thermofield double state, I can transform this state by a unit tree which basically shifts HL and HR. Then that's a different state, which is not the which would not be the same as just the time evolution of the states where so I have something like that in mind. So suppose you have thermofield double state, so I can shift the time slice like this.
Yes.
And that would be a different state compared to just doing a time evolution, which will give you something like this.
Okay.
So so this I think is similar to this kind of a time evolution. Yeah.
Okay, maybe we should discuss later. Yeah.
But in any case, once we add matter, then we have the same problem. Then we have the problem that we were discussing in the beginning, that you have these semiclassical excitations, and those will definitely could lead to a divergent phase space volume. And we want to understand whether if we impose a condition like this, that we fix the length of the initial time slice, do we get a finite phase space volume? So that's one thing that we want to understand. So let's do that. Okay, so for simplicity, I'll just add the following term to the action. I'm just considering a massive classical, so a massive particles on this background, and right, and once again, very similar to the trajectory of the end of the world brane, what we'll find is that the trajectory of the particle is governed by an equation which is very similar. Now here theta theta would be the relative shift between the end of the world brane trajectory and the particle trajectory. Here we cannot set theta to a particular value anymore. That's a degree of freedom, and R is related to the boost of the particle. Now, right. So we can so this was the end of the world brane. This was the original location of the horizon, but now we have added some particle, let's say something like this. And what this will do is basically, first of all, since I'm working in the same coordinate system as earlier, so first of all what it will do is it will shift the location of the bifurcate point, so it will move out. And this will be the new boundary. This will be the new horizon. And we can compute exactly what this shift is. That's one effect of introducing a particle. And once we include the back reactions. So the way we find that out is basically we have some dilettante solution on the left, some dilettante solution on the right. And we know the solution on the left, it wouldn't change, it's the same as before, but on the right, we will obtain by basically matching the solutions. So as I was discussing earlier, so there would be a jump in the discontinuity of the derivative of dilettante that would be proportional to the mass of this particle. And that way we can obtain the solution in this region. And from that, we can obtain the length of the mean length of the geometry or the energy and so on. So I'll just write down the answer for the Hamiltonian once we include this excitation. So this would be the Hamiltonian when we also have the particle excitation. And note here the point that we were discussing earlier, that you could have excitations which in fact lower the energy as measured from the boundary. And that would be true when this whole term is positive. And we can check, I'll not explain here now, but you can check that whenever that's the case, the particle trajectory is always behind the horizon. So they are always hidden from the exterior, which is consistent with our discussion in the beginning. Right, so this is the Hamiltonian. Now, clearly, here you would agree that the phase space volume is just divergent if we just impose that the Hamiltonian is fixed. The reason being, so the divergence will basically come from, could come from various regions. So one would be when phi h is large, and when r is close to 1. So I mean, note that r close to 1 is basically boost of the particle being infinite. We can write down the symplectic form. We can do this more precisely, but these would be the regimes which will give you divergence in the phase space volume. So you can take phi h to be large and also simultaneously take r to be close in a way that the Hamiltonian doesn't change much. That would basically be the usual semi-classical excitations behind the horizon that will overcome the Wittgenstein-Hawking entropy. Is that point clear?
The phi h is the value of phi at the horizon.
It's value, not the horizon. It's not the horizon anymore because the horizon has shifted. This phi h is the same as the phi h earlier.
So it's the phi h without the particle present.
Without the particle, yes. Yes. Right. All right. So now we want to understand whether if we fix the length of the initial slice as well, do we get a finite phase space volume? So first of all, it's unclear that we would, right? Because even if you fix the length of the initial slice, at late times the length will grow. At late times you would imagine that you can add as many excitations or as many particles. So I'm doing one particle here, but you could have added many more particles. So at late times you could imagine that you could add these particle excitations without and that should lead to a divergent phase space. But in fact, if we include the back reaction of the particle, that's not the case, because what happens is that if you look at the regulated length with one particle, it's slightly long formula, but it's pretty much what we had earlier with some modifications. So this would be the new length once we include the back reaction. So this would be the length of, for instance, a slice which starts here and falls perpendicular to orthogonally to the end of the whole brane. Now, this part of the length, so I can split this length in two parts, L1 and L2. So let me call this part L1. So that part is always lower bounded by a finite number. So L1 is always greater than equal to M, where M is some number. But what happens is that when you try to approach these regions in the phase space, where phi h is large or r is close to 1, this term becomes extremely small, and that's why the length of these slices become extremely large. In fact, what we can do is we can compute the minimum length of so minimum length as a function of t naught of this in this limit, and what we find is that this goes to infinity as phi h goes to infinity or r goes to plus minus 1. So, I mean, if we look at this regime, what happens is that the bifurcation point actually moves not to some finite value, but it actually moves very close to this point, this region. So all the exterior is now in the original coordinate system is here, and all the lengths becomes extremely large. So if we impose the condition on the that the minimum length that the length of the initial slice is finite, then clearly these kinds of configurations would be excluded because the minimum length is infinite. So all lengths basically is much larger than the condition that you imposed. And that's just because of the back reaction of the particle. Right. So when we try to compute the phase space volume with this extra condition, we'll find that it's finite. And here we did not have to include any UV regulator by hand. It just automatically happened because of the back reaction. Is this point okay? If there are questions.
So this is some constraint you imposed by hand?
Right now, this is some constraint I imposed by hand. Right. Yeah.
Are you trying to hit a particular value of that finite volume that you get?
Not yet, but maybe through some arguments later, yes. So now what I'll do is I'll switch gear and try to find Euclidean solutions, or which could count these configurations where you have fixed the length of the initial slice.
I mean, how do I want to ask this? So is there some, so you say, okay, well, we impose this by hand.
Yes.
Is there some interesting result that comes out if you try to match that length to some measure of the entropy?
Right. So, I mean, we haven't done that completely. The hope would be yes. And the way we'll approach that is basically first. So this was basically a motivation for fixing the length. But now what we'll do is we'll find Euclidean solutions, Euclidean configurations where the length at a particular time slice is fixed, and then try to see what are the geometries so those won't be like the solutions of the Einstein's equation. They would be solutions of the Einstein's equation up to a constraint, and we can try to understand what are the geometries that contribute to the partition function. In fact, let me just write that down now. We'll find that those geometries are in fact trumpet-like geometries, where as you increase length, actually let me just draw the geometries. Let me explain that a little better. So now I'm doing a Euclidean computation of the partition function. So let's say I want to compute a partition function. So this partition function is an integral over the metric, the dividend phi, and g as well. And I can choose a gauge such that so tau is my Euclidean time coordinate. So let's say I impose g tau sigma is 0, and I want to look at saddles which have a particular temperature at the boundary. So I periodically identify P tau. Okay, so we can try to do that, but we are going to do that in a slightly different way. We'll include a delta function where the length of some initial slice is fixed. So you include a delta function like this, and I mean, if we do an integral over L0, then So if you do this integral, then this is basically just giving us 1. So I'm really not changing anything. But what I want to do is I want to interchange the order of the integral. I want to first find the saddle corresponding to this part, and then later do the L integral. I mean, you could argue that that whether or not this is a well-defined thing to do, but I mean, we want to do this because what we find is that if we fix the length of the initial slice, we get a finite phase space volume. So what we're expecting is that if we forget about this L0 integral, we should get a partition function which is finite. And in fact, that is the case. So we can try to find out the saddles which will contribute one. So what we can do is we can exponentiate this. We can include a Lagrange multiplier, and we can vary over the Lagrange multiplier as well and try to find the saddles. And the saddles will look basically like this. So the metric. So this is the sigma direction. This is the tau direction, and the length of the interior circle is, let's say, b. So this is a parameter which would be related to this length. In fact, when b is small, the length of the initial slice is essentially log of 1/b. Some corrections. So if you're looking at finite length saddles, or by that I mean that the length at some chosen initial time slice is finite, then we get a very well-defined geometry, and then we can consider like one loop corrections of the matter. On top of this, everything will be finite, everything will be nice. But if we take L0 to infinity, if we take the length of the initial slice to large, then what happens is that the inner circle shrinks. So b goes to 0. So when b goes to 0, L0 goes to infinity. So the contribution of the matter determinant will basically blow up. I mean, so the contribution to the partition function would be something like something of this order, and that would be the divergence that we will interpret as the divergence in the in the partition function. So it's basically coming from this small b to g. Now, I mean, if you believe this, then what I'm saying is that there's a potential for UV corrections to kick in. For instance, I mean, if we were in high dimensions, we could have like strings winding around this, which could cut off the integral at some point. But so we started with a problem where it didn't seem clear at all what the UV corrections could be that could change the computation of the partition function or of the number of degrees of freedom. But what we are saying is that if you think of computing the partition function in this way, where you first impose this constraint and then integrate over the constraint, then there is at least there's a scope of UV corrections kicking in because the local temperature in the interior is going to infinity for these constrained saddles. Is this part clear? Yeah.
Maybe a naive question. Like, what did this thing, like you're adding this mass deformation? You could have done this without going into this picture, right? I mean,
yes. So that was to motivate that. So I mean, I could have started with this.
yeah, like
Right. I could have forgotten about
okay.
that.
So
But I wanted to so that's a separate Lorentzian calculation for the phase space, which is meant to convince you why doing this might be a good idea. Right.
For this picture of trumpet, the left circle is the end of word brain.
Oh, right, I should have specified that. Sorry about that. So this is the end of the word brain, this is the ADS boundary.
Then where's the horizon?
This is the Euclidean solution. There's no horizon.
But for example, for Schwarzschild black hole, even the Euclidean solution has horizon at the tip of the cigar. So what the analog in this picture?
I'm not sure if there's an analog for horizon in this picture. It's not clear to me.
Isn't the geometry something more like the Poincare disk where you've cut a hole out of the center of it? And the limit you're interested in is something like taking the size of that hole to 0?
Isn't that similar to, that's the same thing, right? I mean,
No, it's a question of what the extrinsic curvature is on the boundary. It's related to your parameter mu.
here,
Yeah. So
yeah,
it's a question of sort of whether you're in the Poincare patch or the global patch of ADS2.
we are in the global patch, so I have not explained you how these solutions look like, but we can impose the
I guess the invariant way to ask my question is, what's the holonomy of the connection around this circle? I guess it's hyperbolic.
would it help if I give you the metric?
Yes. Basically, the question of is what you cut out a little piece of a cylinder or hyperbolic cylinder, or is it a piece of the plane?
So here I'm not specifying where the ADS boundary is located. I mean, you could have observed B in tau, but that will change the location of the ADS boundary. I'm just giving you the metric.
And the end of the world brain is located at sigma equals where?
Right. I think it's pi over 2.
To get the Lorentzian signature, do we wake rotate tau? Do we wake rotate tau to get the Lorentzian signature?
I mean, I'm not sure what that would mean.
I don't think so, right? Because the Lorentzian geometry has a horizon.
Yeah, it
Whose
has.
loop rotation would give 0 size.
Yeah.
So this is somehow some solution where you stuck the end of the world brain outside the horizon.
Yeah, I'm not sure if we can interpret where the horizon is in the solution. It's just some Euclidean solution where, where you just constrained it.
I think it would be helpful for me to understand the big picture about what you are saying. Are you saying that it's a principle that we should fix L naught when computing entropy, or what exact, or that top-down constructions will always yield that, or with some higher derivative correction or something like that? What exactly are you?
So, yeah, so it's right now it's basically basically a new way to compute the infinite partition function. So this integral would still give you infinity if you integrate over the length, which is basically same as integrating over b. But now you could ask what generic UV features would change the. So this is the part that we haven't done, but this could be one potential question. So what generic UV features could change this computation, could regulate this computation? So if we consider, for instance, some string winding around this time direction, then that potentially can cut off this integral at some finite p. That could be one potential way of changing the computation so that the partition function is now finite. I mean, I'm not claiming that that's what you should do right now, but it's at least at this level, you can think of this as at least a potential bulk way to understand why the partition function could be finite. Which was not clear from the Lorentzian problem that we started with, because there it was not clear why any UV corrections could modify what UV corrections would modify, let's say, the overlap between states. I mean, here, but for instance, if you take this seriously, you could try to compute the overlap between different semi-classical states through Euclidean path integral. There again, you can try to constrain the length and then integrate over the length, and maybe you'll find geometries which are similar to this. And then
those calculations in this infrared, effective theory would give finite answers or infinite answers.
I think it should give finite answers when you it will give.
In the end, it will give infinite answers, right? If you integrate over.
Yes, yes.
So you're just saying some intermediate step has a finite number associated to it.
So all I'm saying is that if we look at some UV corrections, it could be possible that so without really understanding the details of the UV theory, maybe it's possible to try to see why you could get a finite answer. I'm not claiming that you're getting a finite answer now. That would be for future. Another thing for future would be just to try to understand these kinds of solution in high dimensions. So we don't have to work with JT gravity. We can work with, let's say, Schwarzschild black hole in 4 dimensions. We can try to write down find similar saddles, constrained saddles, and do the path integral in a similar way. And even there,
what plays the role of L naught in that discussion?
Would be the volume of the initial size. I mean, that's the part that we haven't fixed completely. That's the part we're trying to figure out, but there are some issues. But yeah, I mean, if the idea goes through, then even there we would expect that that you could get contributions from saddles which have these properties, and even there, and that could be a potential way to introduce UV corrections, which in a seemingly completely semi-classically nice question to begin with. And then the goal would be to see, to explicitly try to see if the overlap between seemingly independent states is non-zero.
Let's first thank Pushkal for the talk.
Can you tell us more about the higher dimensional solutions and what the
Right, I can tell you how you could. Yeah, it's. No, this would be probably off the record because.
Yeah, that's fine.
You want to stop the recording?